So, and this is the next part of our series on hypothesis testing, and we're going to look at a one-tailed test about a population mean. And in this case, the standard deviation is known. Now, the relevance of those two statements will become clear after a while, because we'll sort of deal with other variants of those two situations. Now, here's an example, and the response times for a random sample of 40 medical emergencies were tabulated, so just make a note of that. And the sample mean was 13.25. Actually, over here, let's just make a quick note of that. It's good to sort of, as you go along, keep track of all the information you're given. So down here, let's write down here, n equals 40, and x bar is equal to 13.25. So sample size and sample mean. Now the population standard deviation is believed to be 3.2. So let's make a note of that as well. Population standard deviation is sigma 3.2. The EMS director wants to perform a hypothesis test with a level of 0.05. Let's make a note of that as well. Alpha equals 0.05. To determine whether the service goal of 12 minutes or less is being achieved. Okay. So, first step is we develop the hypothesis. Now, I've sort of developed this hypothesis previously in a other previous presentation, so I'm going to just suffice to say that the null hypothesis is that the population mean, mu, is the population mean, is less than or equal to 12. Okay, the alternative hypothesis is that it's greater than 12. So this is good, this is bad. Okay, now essentially what we're going to do is see, does the evidence support this null hypothesis. Remember, the sample mean was 13.25. Okay, so x bar. So it's just like, what can we think about these null hypotheses given that the sample mean was 13.25 and the rest of the information? Specify the level of significance. Alpha equals 0.05. Great. Now compute the test statistic. Okay. Now, the test statistic is, again, I've mentioned this a few times, so it's worth mentioning again, is the point estimate minus the expected value under the null hypothesis. I'm just going to call that null value for short. That's really not a good name, because that really means something completely different in computer science. But it's just the full name, you would say expected value under the null hypothesis. And that is divided by the standard error. Whoops, standard error. Okay. Now let's just sort of see what the this is the point estimate here is the sample mean. The standard error here is this part here. It is the standard deviation divided by the square root of the sample size, sigma divided by the square root of n. Okay. Under the null hypothesis, we expect a mean of 12. So the expected value under the null hypothesis is mu, and that's equal to 12. So that's that there. And we piece it all together. So the standard error is 3.2 divided by the square root of 40. Remember that in the previous slide that the sample size was 40 and the standard deviation was 3.2. So that's how that comes about. Now this is a bit of calculation, a bit of calculator work. 13.25 minus 12 divided by 3.2 divided by the square root of 40. So the test statistic is 2.47. Now in some cases that's like some situations people refer to that as the signal to noise ratio. Okay. Now p-value approach. Compute the p-value So for a test statistic z equals 2.47, the cumulative probability is 0.9932, and 1 minus the cumulative probability is 1.9937. How did I come up with that? Essentially what I'm going to do is I'm going to go to the Z tables. Okay. The standard normal tables, which you should be using for you should be familiar with after dealing with the normal distribution. Now I go to line 2.4, row 2.4. So let's go there, and I go over to the column .07. See that 7 there? So that is 0.07. So this is just a sort of how I use the statistical tables, and that will give me an answer of 0.9932. Okay, that means that the probability of a z value being less than 2.47, less than or equal to 2.47, is 0.9932. And we want the complement of that, because that is what the p-value is. It's the complement of this. It's the probability of z value being greater than the test statistic. So 1 minus that is simply a complement, and we get a p-value of 0.0068. So that's the p-value there. Now, determine whether to reject the H0, the null hypothesis. Because the p-value equals 0.0068, which is less than 5%, 0.05, we reject the null hypothesis. Okay, so small p-value, reject the null hypothesis. So we are at least 95% confident that Metro EMS is not meeting the response goal of 12 minutes. In fact, not. You can almost sort of say it. We could just by this, you can almost guess that it's 99% even. Anyway, but we're asked for 95%, so we'll stick with that. Okay. That's done out there graphically. It's always a good idea to do this out graphically. So let's see now. This is the rejection region here, and there we go. Get a pen going. Whoops. My pen is broken. So anyway, this is the rejection region here, and what we were interested in is the fact that the p-value is less than the size of the rejection region. Also, what we have, there we go, finally. There we have, the rejection region is also, the threshold for the rejection region is 1.645, and the test statistic is beyond that threshold. So this here is the rejection region, and the test statistic is inside that rejection region. That's the test statistic there, and that's the threshold for the test statistic is the critical value. A critical value there, test statistic there. Okay. Now, we're going to use the critical value approach here. I've sort of came about with some of this stuff already. Determine the critical value for the rejection rule. Alpha equals 0.05. Just as a remark, actually, it's always well worth stating this again and again. This was a one-tailed test. We had greater than in the null hypothesis, or the alternative hypothesis, and we had less than or equal to in the alternative. So, sorry, less than or equal to the null hypothesis, greater than in the alternative hypothesis. That means it was a one-tailed test. Now, alpha and one-tailed test, that means the critical value there is 1.645. Okay, and we reject the null hypothesis if the test statistic is greater than the critical value. In this case it was. We've seen that in the last slide, but I just mentioned it again. Now, because 2.47 is greater than 1.645, we reject the null hypothesis. So that is that one there. It's again, I'm just sort of repeating what I said in the last slide. And I will leave it there. So this is where I'll start the next presentation.